Quiet down, chipmunks. Quiet down, chipmunks. Quiet down, chipmunks. Okay, now what we're going to do in Unit 3, Lesson 6 is look at Cauchy-Euler equations. So these are linear differential equations with coefficients that are constant times the power of x that multiplies the derivative of the same order. So in other words, if you have an nth derivative of y, you're going to have it multiplied by x to the n and a constant in front of that. And you're going to have, for the n minus first derivative of y, you're going to have x to the n minus 1. So here would be a typical second order Cauchy-Euler equation, a number times x squared y double prime plus a number times x times y prime plus a number times y equal to 0. Actually, that's a homogeneous. And for a homogeneous Cauchy-Euler, what do you think would be a good guess?
I really don't know.
Well, a good guess might be something like x to the m power. Since we got these polynomials multiplying derivatives, that might be it. So, if that is our guess, then y prime would be m times x to the m minus 1. And y double prime means we got to take a derivative of this, would be m times m minus 1 times x to the m minus 2. And when we substitute back into our homogeneous linear differential equation, Cauchy-Euler equation, what do you think you get then?
I really don't know.
Well, what you get then is ax squared times m minus 1 times x to the m minus 2 plus bx times m times x to the m minus 1 plus c times x to the m, and that is equal to 0.
I sincerely hope so.
Yes. Well, so what good did that do us? Here's where you must be careful. This is different from solving a homogeneous linear second order equation, because it looks like you would use something like the quadratic formula, but you don't. What happens is this x squared times this x to the m minus 2 just gives us x to the m. Similarly, x times x to the m minus 1 gives us x to the m, and we already have an x to the m in this term, and we can just cancel that out. But what we have remaining is a times m squared minus m plus b times m plus c. Well, that means we have a quadratic equation, but the coefficients aren't the a, b, and c like we expect from the original. They're going to be a for the m squared, yes, but we're going to have b minus a times m. This b minus this a, see, times m, and then plus the c. So, little typo there. Anyway, that is the famous formula. The quadratic formula will solve that, but remember, it's not straight a, b, and c like you expect, because what we would normally consider the b, the middle term, is going to be b minus a. So now we will get 3 cases based on the nature of the roots. So, if m1 and m2 are real and distinct, then the general solution of the homogeneous equation is just c1 x to the m1 plus c2 x to the m2, and it couldn't get easier than that.
I sincerely hope so.
Okay, case 2. If there's a repeated root m, and we know one solution to be y1 equals c1 x to the m1, then we use the method of reduction of order, Unit 3, Lesson 1, dividing first by ax squared, and this turns our differential equation into one we're used to handling, and we'll use the reduction of order method, or should we call it variation of parameters? It's really kind of the same thing. So y2 equals x to the m1. Well, you should know that e to the integral negative p of x dx over x m1 squared dx, so we get x to the m1, or x to the m1 times, well, this is going to be e to the negative b over a times ln of x, which is just x to the negative b over a divided by x to the 2m. And so that's x to the m times x to the negative ba minus 2m, and what is that equal to? Well, that is equal to x to the m1 times x to the negative b over a times x to the negative 2m1 dx, which is, it's complicated. X to the m1 times x to the negative b over 2a minus 2 times negative b minus a over 2a dx. And you're wondering, well, where did that come from? Well, that came from the fact that m1, if it's a double root, then the b squared minus 4ac, well, guess what? Our m1 will be negative b minus a over 2a. That's kind of like what the double root would be. Let me take you through that again. If we have a double root, it's, from the quadratic formula, it's going to be negative b, negative this, over 2a. If there is a double root. So I just replaced that where the 2m1 is. And now, look, we can do some algebra with all this. So that's x to the negative b over a times, see the 2's cancel, so times b minus a. And how do you handle something like this? You would add the exponents, right? And so that means we get x to the m1 times x to the, look at this. Add this exponent to this exponent. What do we actually get? Negative 1. Because we get negative a over a. Everything else is gone. So, and of course the integral of x to the negative 1 is ln of x. So x to the m1 times ln of x. So that's our second linearly independent solution from our double root. We get x to the m1 is one of them. X to the m1 times ln of x is the other one. That was sneaky. Check out, add these two exponents together in your head. Negative b over a plus b minus a over a. Do you see why you get negative 1? Because the negative b and the positive b cancel out, so we just get negative a over a. Negative 1. So that's our second linearly independent solution, and that is our complementary solution. Now, it's worse. It could get worse. So now what? Okay. Well, suppose we get imaginary numbers for the roots. Then m1 is a plus bi, m2 is a minus bi. And now what do you think? Yes, well, we could start out by saying the general solution c1 x to the a plus bi plus c2 x to the a minus bi, but imaginary exponents would cause us some difficulties. So we know the e to the bi is cosine of b plus I sine of b, and further that x equals e to the ln of x. So we'll make x to the bi x to the ln of x times bi. Sorry, we'll make x to the bi e to the ln of x times bi. So that means we'll have cosine of b times ln of x plus I times the sine of b times the ln of x. So now our solution is, or can be rewritten, x to the a times c1 times cosine of b times ln of x times plus c2 times sine of b times ln of x. Wow. So now that we know about the three cases, let's go ahead and solve some of these. Yes, so now let's see how we can apply this, and I don't think it'll be all that bad.